Okay guys, let's take a look at today's lesson. Yesterday we learned a graphic way to approximate a differential equation, the solution of a differential equation. We learned to do that by slope fields using little slope lines using a visual approximation technique. This one, Euler's method, is a numeric approximation technique where we're still approximating the solution. We are simply using a different technique, a different approximation technique. And they do love Euler's method. So, and linear approximation. Those are just, approximating techniques are really important in math. Since we talked about it before, we can't solve by hand every differential equation. There has to be approximation techniques to come up with solutions. So let's take a look at this first piece, the error. Since approximation techniques are really important, so is our error, or percent error. And we'll be looking at this in detail all semester in our approximation techniques. So absolute error is going to be the exact value minus approximation, the absolute value of that. And that just kind of makes logical sense. If you want to figure out how good your estimate is, you would take the real thing and subtract the estimate from it, and then you would figure out, your error. If you want a percent error, you would simply just, turn it into a percent. So I think one of the questions on the daily work asks you to approximate the error. This is definitely a calculator lesson. You really need your calculator for these kind of computations. These aren't the kind of things you really want to do in your head or on scratch paper. So I'm going to kind of go through the steps fairly slowly. We had a little bit of difficult time with this. It takes some getting used to do this technique. I think once you've done it a few times, it becomes more comfortable. But I'm going to kind of walk you through real slow what you need and how it works. So in order to use Euler's method, you need a differential equation and you need an initial condition. You need those two things to be able to use Euler's method. So let's talk about what this means, because they use it down here. It's y prime, so dy dx equals f of xy. Well, f of xy means that you substitute those values in and get an answer, right? The x and the y value into the function, you get an answer. Notice that they're calling this y prime and they're using it down here. So I think the notation is a little bit strange, a little bit perhaps confusing to students. This f of x naught y naught means the value of the differential equation at a point. That's what it means. So this piece is the value of the differential equation at a point. Alright, so that's what we need. We need a differential equation and we need an initial condition. And then what we do, our first step, is to decide what our increment, our delta x, they call it an increment or a step size, is. Now the vast majority of the time you're not going to be able to pick. They're going to give you circumstances where it forces the step size to be a certain thing. So we'll go through this. This is really kind of abstract, but I want to take you through the formulas. You will certainly be able to do these in your head, but I want to show you what the formulas mean. So we're starting out with an x naught. Okay, to get our x1, we would take our original x, our x naught, and we would add the increment to it. Let's say we're going from an x of 1 to an x of 2, and they want us to use 2 steps or 2 increments. We're going from 1 to 2 and we only get to go 2 steps. That means that our delta x would be 1/2, right? 1/2 and then 1/2, and that would get us to 2. So this is it in basically in a formula form. To get our first x1, we take our original x and we add our increment to it. In the example I just gave you, we would add 1/2 to it. Okay, to get our second x, we would take our first x and we would add the increment to it again. And we would just do this however many steps we're asked to do. And typically, it's no more than 2 or 3 steps. You're not going to be doing this for 10 steps or something like that. It's usually just a few steps to make sure you know how to do Euler's method. All right, once we take care of that, so we have our original x, we figure out what our increment is, we have our x1 and x2 and however many x's we're supposed to have, then we are working on the computation. So, to get our first approximate y value, we take our original y value, we take the original point and substitute it in the differential equation to get that value, and then we multiply that by the increment. I'm going to say that one more time. To get our first approximated y value, we take our original y value and add basically this differential equation. We plug in the original point, the x naught y naught, into the differential equation. We get a number, and we multiply that number by the increment, whatever our increment happens to be. And then we would complete that however many steps we're required to. So let's say we need a second y value. It's a 2-step. I would take the one I found here, my y1, and I would add to that. Now I'm going to use my new x and y value to put into the derivative, to put that value here, and then I'm going to multiply by the increment. It's like a chain. It just keeps going as long as you need it to go. Let's look at over here what it looks like visually. So here's my original x naught y naught value, and here is my increment. You know, it's overlaid on a slope field, I guess, just for demonstration techniques or purposes. So this is actually, you know, would go with approximation. The visual approximation of the slope field would be this blue line. These are showing this Euler technique. What we do is we take our increment and do this formula right here, and we get our first approximation value. They're like little tiny, you can think of them as like little tiny tangent lines if you want to. You know, they're just little segments. And then we keep going. We use that to get this one and keep stepping. Okay? So that is Euler's method. Let's do an example. Okay, yes. So let's see what we're given the differential equation. Okay, so we have this that we need. We have our differential equation. And let y equals f of x be the particular solution to the given differential equation with the initial condition. Okay, great. We have the two things that we need. We have a differential equation and we have an initial condition. So they want us to use Euler's method. They want us to start at an x of 4. So this would be my x naught. And even if they didn't tell me to start at an x of 4, I need to know that's where I start. How would I know that that's where I start? Because that's the point you're given, right? You're going to start at the point that you're given, whatever that point is. So my initial x value in this case is 4. I'm supposed to do 2 steps of equal size, and I'm supposed to approximate f of 4.2. Notice they don't tell me what my increment is, but they put such restrictions on me that, I mean, it would be the same for all of us. If we're starting at a 4 and we need to get a 4.2 and we need an increment to only 2 steps, it's going to be 0.1, right? I mean, that's what it's going to be. And so that's the typical thing that you will get in a problem, is they will restrict it in such a way that you're going to figure out the increment. Now I'm going to take you through this formula just so you can see how the formula works. We already figured out what the x's are, but I'm just going to show that, demonstrate the formula. So to get my x1, to get my x1, I would take my x naught, and my x naught was 4, and I would add to it my increment, and I think we agreed the increment was 0.1. So this is f of 4.1 is the same thing as x1, and that's going to be x equals, this is my x1, not my y. So my x1 is 4 plus 0.1, which is 4.1. And my x2, I take my x1 and I add the increment again, and I get 4.2. You certainly are not required to write it out in formulaic form. I mean, you can do that in your head, but I wanted to show you what this means. That's what it means in abstract. Okay, so that takes care of step 1. Right here is step 1. Step 2 is where we start dealing with the y values. So to get my y1 is, I'm going to take my y0, which was -1, and I'm going to add to it my derivative at the initial point. So my derivative is right here. My derivative happens to be x plus y. So my x value of my original point is 4, plus my y value of my original point is -1. And now I'm supposed to multiply that by my increment. I use my calculator, and I get -0.7. Now let me caution you here, just right now, because I had several students earlier today just automatically put in this derivative, the x plus the y. Okay, y is the only reason that right here I did my original x plus y. Because that's the derivative, right? If that wasn't the derivative, I wouldn't have done that. What if the derivative was 2x? Then I would have ignored the y, right? And I've done 2 times my x value. So please, the reason this is x plus y is because that's what my derivative, my differential equation says. It's not a pattern or something that you're supposed to follow all the time. Okay, it's just that this is my differential equation. So now that I have my first step, I need my second step, right? Y2. Question? We okay? Okay. So my y2, I'm going to take my, again, my y1, the y that I just found, the -0.7, and I'm going to add to it. Now, which point am I going to put in my differential equation? x1, y1. I'm going to put the point that I found into my differential equation. And so, and again, my differential equation is x plus y. That's why I'm doing x plus y. So my new x was 4.1, and my new y is -0.7. So I add those together, and I multiply it by the increment. And of course, this is in your calculator, and I get a -0.36. So my f of 4.2 is -0.36, and that's my approximation. So that's my approximation technique. Okay. Actually, that using the x2 in the formula, no. The x2 would be, I mean, you mean the y2? Or both? No, you don't. And that is a good question, because sometimes this is given to you in table form, and some students want to use this last number. It's really not ever used. That's what we have found. We're always using the information before us to get the new. We're never using what we're at. So, good question. Yes? Yes, and that's another good question, because that's one of your daily works asked you to do percent error. So if we wanted to find percent error, we would have to take this differential equation and solve it like we have been, get the actual for real equation, sub in the 4.2, and then compare the numbers. And use your calculator, right? You're going to be using your calculator for all of these. Okay? Are we okay? All right. Great.